All right, so who wants to tell me what has to happen if this reaction is going to occur? What has to happen? George, what did you call?
Have to hit each other with enough kinetic energy and be oriented in the right way.
Okay, so it's about kinetic energy. Particles have to hit each other hard enough, and particles have to hit each other in the right orientation. How many particles, though? How many particles have to hit each other for this to happen? 7. Yeah, 2 plus 4, 6 plus another one. What's the likelihood that 7 particles are going to smash into each other at the right orientation with the right kinetic energy?
Unlikely.
Yeah, very unlikely that it's going to happen. So how does something like this even happen? Because this is an actual reaction. How does this happen? Ooh, yeah, maybe it doesn't happen all at once, right? Maybe it happens in steps or in stages, as George pointed out. And that's what we're going to cover next, is something called reaction mechanism. So we've been lying to you when we've been putting this in front of you and saying, oh, you just add all the reactants together and you get a product. Not quite that simple. Okay, so it's kind of, we've been living a lie. It actually happens in stages. So really what we're going to talk about is reaction mechanisms. And it's not just like, okay, all these 7 things collide together and boom, we have products. It's really a sequence of steps. All right, so first there's 2 things collide, and maybe 2 other things collide, and it's a series of steps that actually makes the reaction happen, and that's what we call a reaction mechanism. So it's not just one, some things collide, some things it's just like A plus B, synthesis reaction, but other things are more complicated. So reaction mechanisms are really what we're talking about, a series of steps, and each step represents some collisions that have to happen in a certain order, and you put those steps together, and that's what we call the overall reaction, right? So that reaction that we saw there with the 7 things colliding is really kind of a sequence that has to happen in order. Okay? So we're going to look at a reaction instead of the way we've been looking at it. We're actually looking at reactions in Chem 1. We just started. We're going to look at them a little bit differently. We're going to look at them as a series of little steps or elementary steps or elementary reactions. So each step is an elementary reaction. You'll see what I'm talking about here in a minute. So we see how many things have to collide in each step. So there's just some vocabulary here. Unimolecular, right? Like a unicycle. Uni means 1. So what's a unimolecular collision? What does that mean? Can something collide with itself? No, but something can certainly decompose, right? You can have 1 reactant that turns into 2 or more products. So unimolecular means something is going to decompose. Bimolecular means 2 molecules crashing into each other. What's 3? Yeah, they call it termolecular instead of trimolecular. I know, right? And it goes on, but it's not likely. It's not likely that you're going to have much more than 3 things colliding at the same time. It's just not likely for that to happen. But the idea here is that we can write the rate law. So again, we can say rate equals K times the concentration of, let's say it's unimolecular, right? 1 reactant to whatever order it's in, which is what we did last week. Or if it's 2 things colliding, we can write the rate law for a bimolecular collision, bimolecular step. So that's what we're going to do, is we're going to write rate laws, but instead of writing it for the whole thing, we're going to write it for each step at a time. All right, so again, here you go, unimolecular, bimolecular. It just kind of breaks it down. This is in the notes. Notice that bimolecular could be 2 things colliding with each other. Right. So for example, if you have chlorine plus chlorine, what does chlorine plus chlorine make? Chlorine, right? That is a bimolecular collision. It's 2 chlorine ions that have to form to make this, and then maybe this starts something else. And so again, we're not going to get past termolecular just because it's not something that's likely to happen, but this should look familiar to you at this point. Yep. Yep. Rates. Yep. Okay. All right. Oops, what did that say? Yeah, so termolecular, not likely to happen, but we got them up there anyway. And so, couple more words. When we start this going, we might make something that doesn't make it out of the reaction. That's called an intermediate. It makes kind of makes sense. I'll show you an example of this. Intermediates form as products, but then get used up. Okay, so it's kind of a temporary situation where you make something in one step, use it up later on, and it doesn't come out of the reaction. It's a little easier to see when we actually have reactants. A catalyst is something that we put into the reaction, but then it comes back out of the reaction. So it might be used up, but then it gets reformed. Okay, so we'll see that as well. So just keep in mind intermediates and catalysts, because that's the kind of question they'll ask you. They'll give you a series of steps and say which one's the intermediate, which ones are the catalysts. All right, so it's your first practice. Couple things, the steps of each mechanism. When we add up the steps, we have to add it up to the total reaction. Each one of the steps has to be balanced. The whole thing has to be balanced. We need to identify intermediates. And I'll just leave this here. We're going to circle the intermediates. How about that? We'll do it that way so everybody does the same thing. Let's take a look. This is the one you have. So somebody proposes this reaction, right? They see a reaction. They say it can't be all happening at the same time. And they're looking at the reaction as it happens. They notice that we formed this product. They measured it somehow, but then they noticed it went away. It didn't show up at the end, right? So this is telling us that something got made and then it got used up. So what would we call that? That's the intermediate, right? So we're going to circle that. Are there any other intermediates that you see? Yeah, in step 2, it forms Y, and then Y is immediately used up in step 3. Now, it doesn't have to be one step to the next. We could have used up Z down here. The idea is that somewhere in this whole reaction, we made something that later got used up. So what's the overall reaction? So what did we put in? What are the reactants in this? A plus B. All right, so A plus B. We didn't use those up. I mean, we did use those up. What about this? That's also A. Very good. So, is that a different A or is it the same A?
Same A. Different A.
It's another A, right? It's still A, right? But this is another A. So really what we're saying is we're putting 2 moles of A in. The first one's getting used up here. The second one doesn't get used till the second step, but we're still putting in 2 moles of A, a mole of B, and what else do we have to put in to make this reaction happen? We have to put in a mole of C, and our total product is D. Now, this is a tetramolecular process. This would have had to have 4 things collide. Not going to happen, but it could certainly happen like this. Okay? So that's what we're talking about when we do these. Some of them are going to ask you for the overall reaction. Notice how the intermediates dropped out. The catalysts will also drop out, but you have to identify which ones they are. So I'm just going to let you practice this. Try it on your own. It's a little tricky. Pay attention to what's going on, and we'll take about 10 or 15 minutes to do this. And I'm going to stop recording again. All right. All right. Let's get back to this now. All right. So you guys drive. Who's ever driven through a toll plaza? Like to go through a bridge or something? Do you have to slow down to get? Yeah, right. If you go to a toll plaza, you have to slow down. Now, this is the analogy. Imagine there's 2 toll plazas, one after the other, right? So the traffic backs up at the first one. What happens on the second one? Not, because everybody's backed up here, so you just kind of flow right through there, right? Now, what could also happen is if you have 2 in a row, you could back up at the second one, which means these guys are just kind of flying through here and they stop at the second one. So one of these toll plazas is going to limit the flow of traffic, right? You can only go as fast as the slowest one of these. That makes sense, right? One of these is going to be the slowest and determine how quickly you can get through there. The same thing happens when we break up a reaction into steps, because one of the steps is going to be slower than the other one, which means that step will tell you how fast the whole reaction goes. You can only go as fast as the slowest step. So we call that the rate determining step. Sometimes it's called the rate, what's the other thing called? Yeah, rate determining or rate producing step, I guess. But basically what we're saying is if you look at a set of steps, they're going to tell you fast, slow, fast, or slow, fast, fast, or one of them is going to be slow. That's the rate limiting step or the rate determining step. Yeah. So if you get a question that says, what is the rate determining step? It's always going to be the slow one, and they'll tell you which one that is. All right. So for example, here's a reaction. This is bimolecular. They did some experiments and they found out that this rate law was rate equals this. Rate equals K constant times the concentration of NO2 squared. The concentration of NO2, NO2 is a second order reactant. Okay. However, because you have to have this for the reaction to happen, that can't mean that you can't have this. You have to have carbon monoxide. We just don't depend on its concentration for this to happen. So because of this, somebody proposed that this doesn't actually happen by a collision of these two. It happens in two steps. So they're going to propose, here's the two steps that are happening. Step one, you put in some NO2, it collides with itself, it makes these products, and then these products, one of these products will combine with CO to give us the products we want. So those are the two steps. Just digest them for a second. Any intermediates or catalysts here? Yeah, NO3 got formed from the collision of the first two, and it was immediately used up for step two. Okay, so this is the intermediate. Now, what else do we see is happening? What's that? Yeah, there's a catalyst because we're putting in 2 moles of NO2, but 1 mole of NO2 is just used for this first collision, and then it's coming back out as a product in the second step. So we're only really consuming 1 mole of this NO2, which is why we only have 1 mole of NO2 up here. So really what we're saying is, here's our overall reaction, right? NO2 plus CO gives us these products. The first step is the slow one. So which one's the rate determining step? The first one, the slow one. We can only make these products as fast as this step happens. If this happens, like 1 mole a year, that's as fast as the reaction is going to happen. If it happens 1 mole per second, we're going to make it as fast as this happens. All right, so let's take a look and see what we can do with this. Oops. Oh, yeah, by the way, how come the rate law doesn't include CO?
Okay.
Some of you are not paying attention and you're going to be asking all kinds of crazy questions later. How come CO does not appear in the rate law? Because it's not part of the slow step. It's not what's making this reaction happen. This reaction depends on the concentration of the dates because this is the slow step. Doesn't matter how much of this we put in, it's going to be determined by these. Yeah. Yeah. You can't figure that out on your own. Yeah. It'll tell you this is the, not just you, but I mean, none of you, none of me. We can't figure this out. It'll break down and say, this is the proposed mechanism and this is the slow and the fast one. All right. So let's take a look and see, how do we write the rate law for this reaction? Well, basically what we're going to do, we go back. Hang on. Whoops. This is the harder stuff here. All right. So what we're going to do, if we want to write the rate law for this reaction overall, we have to write the rate law for the slow step because that's the one that's driving the whole thing. So how do we write the rate law for this? Rate equals K times what? What does this depend on? Concentration of these reactants. How much does it depend on the concentration of these reactants? There's 2 of them. Not CO2, NO2, sorry. Good catch. And we're going to square that because it depends on the concentration of this twice. And we can do that. We can use these coefficients only if it's an elementary step. We can't do it for this, but we can do it for the elementary step. Yeah? Yeah? Okay. All right. Here's what I'd like you to do before we move on to the really harder stuff. Try 1, 2, 3, and 4. It's asking you things like, what's the slowest step? What's the rate determining step? Write the rate expression. What is the molecularity? Who's going to be the first person to ask me what that means? Molecularity. So this is a termolecular reaction, and they went ahead and experimentally determined the rate law. Okay, so the rate law is found experimentally to be this. Now, what do we know about termolecular reactions? Rare, not likely to happen, right? So what they propose then is saying, all right, even though this looks like they just pulled it straight off of here, it's very unlikely that 3 things are going to mash into each other enough to have enough collisions to make this happen. So they proposed a 2-step reaction, or a 2-step mechanism. Okay? And this is the proposed mechanism. They said the first step is that one of these collides with one of those and makes NOBr2. That's a fast step. That happens pretty quickly. And then what happens is you get the second step where, this product is now used as a reactant. What do we call that? That's an intermediate, right? So this doesn't really show up anywhere in here, but it happens. This combines with the second one of these and forms 2 NOBRs. Now that's our slow step. So which one's determining how fast this goes? Step 2. It's the rate determining step because it's the slow one. So what's the rate law for this reaction? What do I have to do to find a rate law for this reaction? I have to write the rate law for the slow one. So what's the rate law for the slow one? Rate equals K concentration of NOBr2 times the concentration of NO. However, there's no NOBr2 in here, right? So how can we say that this reaction depends on the concentration of something that we're not even putting in? What's up with that? What? What can? You can't. Yeah, exactly. You can't, right? The rate of this reaction has to depend on these reactants, right? It's got to be these reactants to the first or second or 0 power. So this is all well and good, except we can't keep it like this because this is not a reactant that we're even putting in. We're just making it and getting rid of it as an intermediate. Yeah. So we have to figure out how to write the rate expression, this rate expression, with just these reactants. Can we do that? Yes, what? Can we do that?
Yeah.
Yes, we can. All right, so what we have to do then is look at the other ones and say, is there something I can substitute in here, this concentration, that uses these reactants? Okay, so we're doing a little bit of substitution here. We're going to do a little bit of kind of algebra. I don't want to say trickery, but it's going to be a little bit of algebra. So let's take a look here. Here's your overall reaction. So I want to make sure we keep our overall reaction. Now, again, I want to expose you to this today because when we go through it again on Thursday, you'll see it for the second time. It'll make more sense. This is our overall reaction. These are the 2 steps. This is the rate determining step. And we said the rate law for this is this. Now, notice it says rate. This should say rate 2. K2, why K2? Because it's step 2, right? So we're looking at one step at a time. And then what we're going to say is, what can we sub in here that will give us these reactants? So how do we find the concentration of NOBr2? We're going to look at this reaction and say, now this is going to get kind of tricky because we haven't done a lot of equilibrium. If you look at this, you notice it's a reversible reaction. So there's a reaction where NOBr2 turns into these products, right? First step says we make some of this, but then we go back and it reaches an equilibrium. We're going to spend all of Unit 7 talking about equilibrium, but this is a reversible reaction. So we're going to write the rate laws for step 1. Sorry about that. So we're going to write the rate law for step 1. What's the rate law going forward for step 1?
Rate
Rate
equals
1 equals K1
and
NO BR2. And that's rate 1. Now, if this has reached equilibrium, what does equilibrium mean? Equilibrium means we are making product at the same rate that product is being made back into our reactants. So what can we say about rate 1 going forward and rate 2 going backward? I should say rate 1 forward. What can we say about that? Yeah, the rate going forward is the same as the rate going in reverse. And what's the rate law for the reverse reaction? K1 reverse or -1 or whatever you want to call it. Now K2 is this one, times concentration of NOBR. Now let's keep our eye on the price here. What we're trying to do is find this so we can sub it in. Yeah. 2, you're right. Good point. All these examples, it's like they're all BR2 or CL2. So yeah. Okay, so we're going to do a little bit of math work here. All right. So let me go back to this. So basically what we're going to say is because these are constants and because these two rates are equal to each other, we're going to divide both sides by K minus 1, minus 1 being the reverse rate. What's a constant divided by a constant?
1.
No.
Constant.
I mean, if they're the same constant, it's 1. But what if you have a constant divided by a constant?
The constant.
It's constant, yeah. So basically what we're saying is we're coming up with a brand new constant, getting rid of this, and we're saying that the concentration of NOBR2 equals some new constant times these. BR2. And again, the whole goal of this was to substitute this into the rate law for this one. So let me write that rate law again. Rate law for 2, which is our slow determining step, was K2 times the concentration of NOBR2 times the concentration of NO. And I'm going to take this and just sub it right in. So what are we going to get when this is all subbed in? Rate 2, which is the rate of the whole reaction, is K2 times K1 over K minus 1. So here's a question. What's a constant times another constant divided by a constant? It's a constant, right? And that's all it's going to be. Except instead of concentration of NOBR2, we're going to sub this in. So NOBR2 NO. So when we clean that up, I'm going to do it over here. We get rate equals a new constant, the overall constant, which is all these constants smashed together, times the concentration of NO squared times the concentration of BR2. This is the rate of the slowest step expressed in reactants that we can put in. Yeah.
So like the rate of the overall rate is always just like the slowest rate expressed.
It's some function of the slowest one. Yeah. It's not necessarily the exact same number, right? But it's based on the fact that this rate is going this far. Questions? Yeah, Mackenzie. Yeah. So don't get super wrapped up on the K part. Just keep in mind every one of these rates has a constant. So just imagine it's a number, right? Imagine like, for example, this rate was 3 and this rate was 2. And it's always going to be 3 and 2. You could divide it, it's always going to be 3/2, right? No matter what these concentrations are. So the idea here is that you're taking constants, dividing them by constants, multiplying by another constant, but it's always going to be the same constants. So in the end, when you do this, you're gonna experimentally, you're gonna determine what this is, and it's gonna stay there for that temperature. Okay? Questions? You want to try one? That's my question. I want to race it. All right.